Welcome to RT1 Lesson 5. By the end of this lesson, you'll be able to work with Pythagorean triples. Pythagorean triples. So first of all, what are they? It's a set of three positive integers that work in the Pythagorean formula. As I look at this, there are some important things that we need to make sure that we are mindful of. First of all, they must be positive integers. So I can't have anything that's negative. I can't have decimals. I can't have irrational numbers. Secondly, it must work in the Pythagorean formula. Must work in a squared plus b squared equals c squared. And this, of course, we're talking about right triangles as well. Let's talk about some common Pythagorean triples. Here I have a chart with some common ones. Let's first look at the 3, 4, 5. I just want to show you what that looks like. So if I have a right triangle, what that means is that the legs would be 3 and 4, and the hypotenuse would be 5. Remember that hypotenuse is always the longest length. And the reason that it's a Pythagorean triple is because they're all integers, they're all positive integers, and it works in our a squared plus b squared equals c squared formula. So let me show you. 3 squared plus 4 squared is going to equal 5 squared. So we have 9 plus 16, that's going to equal 25. 9 plus 16 is 25, so 25 equals 25. So that's why that is a Pythagorean triple. Now let's look a little bit at this chart. Here we can see that 3, 4, 5, all I do is multiply it by 2 to get to the next one, 6, 8, 10, times 3 to get to the next one, and times 4 to get to the next one. So really, if you can find one Pythagorean triple, you can multiply it and find an infinite number of Pythagorean triples. So let's take a moment to fill in some of the missing numbers. Let's look at this red column here. And I can see that 3 times 4 gave me 12. So now I'm going to do 4 times 4 to get 16 and 5 times 4 to get 20. Now, if I wanted to check my work, I could check by making sure that 12 squared plus 16 squared in fact equals 20 squared. And as you can see here, it does. 12 squared is 144 plus 16 squared, that is 256. And I want to make sure that equals 400. When I add, 400 in fact equals 400. We can now look at the same thing using 5, 12, and 13 as our base Pythagorean theorem triple, if you will. 5 times 2 gave us to 10, so 12 times 2 gave us to 24, and 13 times 2 gave us to 26. I can see for the next one, 5 times 3 gets me to 15, so I'd want to do 12 times 3 to get my missing number of 36, and I can see 13 times 3 gave me 39. Looking at the last one, I can see that 5 times 4 gave me 20, which is the same thing. 12 times 4 is 48. So we're going to do 13 times 4 to get our missing number of 52. And you could check any of these by doing 20 squared plus 48 squared, and you would see that you would indeed get 52 squared. This will work for any Pythagorean triple. So if you find one Pythagorean triple, you can multiply those numbers by any integer, any number, to get another Pythagorean triple. I would like you to use this strategy to fill in the missing numbers for the last two columns. Go ahead and pause the video and then press play to check your work. Go ahead and check. In the blue column, I got 14 and 100, and the green column, 34 and 45. Now, the converse of the Pythagorean theorem is also true. If the legs of the three sides of a triangle satisfy the Pythagorean equation, then we will know that the triangle is a right triangle. So, as I look at a triangle and I know three sides, I could figure out if that triangle is a right triangle by using the Pythagorean theorem. I could look at a squared plus b squared and make sure it equals c squared. And if it does, then the triangle would in fact be a right triangle. I'm going to show you an example here. So let's say I have this triangle and I'm told that the sides are 3, 4, and 5. And I want to know, is this truly a right triangle? I could use the Pythagorean theorem a squared plus b squared equals c squared. And we're using the idea of this converse of the Pythagorean theorem. If these side lengths satisfy the Pythagorean theorem, that'll mean that this triangle is a right triangle. So 3 squared plus 4 squared, does that equal 5 squared? 3 squared is 9, 4 squared is 16, 5 squared is 25. 9 plus 16 is 25. Since 25 is equal to 25, that means that this is a right triangle. Let's go ahead and look at some examples. Let's look at these word problems. So the first one says, how high on a building will a 39-foot high ladder touch if the foot of the ladder is 15 feet from the building? So the first thing we want to do is we want to draw a picture. Let's say that this is our building. And we have a 39-foot ladder that is 15 feet from the building. So the foot of the ladder is 15 feet from the building. And as I mentioned, this ladder is 39 feet long. So what we're trying to identify now is how tall is the building. We can assume here that this is a right triangle because we're going to say that this building was made well and it creates that 90-degree angle. So now we're going to use the Pythagorean theorem to determine how tall our building is. Our building is one of the legs of our right triangle. So let's just call it B and we'll call the other length A. And then 39 is C. So A squared plus B squared equals C squared. I'm going to substitute what I know. 15 squared plus B squared, I don't know that. And then C is 39, so 39 squared. From here, we're going to use our algebra skills. 15 squared is 225. Bring down our plus B squared. 39 squared is 1,521. Then I'd want to subtract 225 from both sides, so I'd get B squared equals 1,296. Then I'm going to square root, and I get B equals 36 feet. And that is the height of our building. On our second example, it says find the amount of fencing in linear feet needed for the perimeter of a rectangular lot with a diagonal length of 13 meters and a side length of 12 meters. So again, the first thing we should do is set up a picture. So I have this rectangular lot. It tells me that the diagonal, which would be this length here, is 13. A side length of 12. We don't know this other side length, and that's what we need to find first. We know that this is a right triangle because it is a rectangle. So again, we're going to use A squared plus B squared plus or equals C squared. And we can say that we have a side length 12. Let's call that our A. Let's call our unknown the B. And then C is the hypotenuse. So we know that that's 13. So 12 squared plus X squared equals 13 squared. We get 144 plus X squared equals 169. I'm going to take 144 away from both sides. So I get X squared equals 25. And I need to take the square root of both sides. So I get X equals 5. So our missing side length is 5. We are not done yet because it asks for the perimeter. So we need to add 12 plus 12 plus 5 plus 5 to get our perimeter, which is 34 meters. I do want to pause here for just a second. If you go back and you realized that the side length was going to be 5 because you knew that 5, 12, 13 is a Pythagorean triple, that's why these Pythagorean triples are so handy. So if you could right away tell me that the side length was 5 because you know it's a Pythagorean triple, that's fine. You didn't need to show all that work of finding the side length to be 5. If you didn't really take us a whole long time either. All right, let's look at some more examples. In these examples, we're looking to see if the following numbers are Pythagorean triples. Let's jump ahead and let's start with the second one, which I'm going to call number 1. And are these following numbers Pythagorean triple? I can right away say no because of the radical symbol. We know that Pythagorean triples have to be integers. So let's remember, if I have a radical, if I have a repeating decimal, if I have just a general decimal at all, then I can right away determine that it is not a Pythagorean triple. So now let's take a look at the next one to the left. So first of all, I see that they're all positive whole integers. And then what I'm going to use is the Pythagorean theorem. And I'm going to use a squared plus b squared. And I'm going to see if it's equal to c squared. Remember, c squared is the hypotenuse, so it always has to be the longest one. So I want to know if 35 squared is equal to 21 squared plus 28 squared. So from here, I'm going to do 28 squared, which is 784, plus 21 squared, which is 441. And I'm going to see if that's equal to 35 squared. 35 squared is 1,225. So I'm going to add 784 and 441 to get 1,225. Since 1,225 is equal to 1,225, that means that, yes, this is a Pythagorean triple. All right, go ahead and color the Pythagorean triples yellow and the non-Pythagorean triples blue. So I'm going to have you do is pause the video, and as you're working on these, some of these you'll see really quickly that they're not Pythagorean triples because they have a decimal or they have a radical. Remember, it has to be integers, okay, in order for it to be Pythagorean triples. If you see integers, then you would need to check using Pythagorean's theorem like we did on the last slide. If you need to pause and rewind and review that a little bit, you can go ahead and do that. Otherwise, pause the video, color the Pythagorean triples yellow and the non-Pythagorean triples blue, and then press play to check your answers. Pause now. Go ahead and check that yours looks like mine. As I look at two of the blue ones in particular, this one and this one were really easy to right away see, yep, I have a radical, yep, I have a decimal. Those cannot be Pythagorean triples. The other ones I would have had to check.